Hi, my name is Gabe Ungab, and this is my lab 3 for Physics 2211. In this lab, I analyzed the orbital motion of a star around a black hole to calculate the mass of the black hole. Then I simulated the motion of a spaceship in orbit around a planet and the moon orbiting around that same star. The purpose of this lab is to build two models via Newton's second law. In part 1, I calculated the mass of the black hole using the net force on the star by the black hole, and in part 2, I found the initial velocity for the spaceship to orbit both the planet and the moon through trial and error. In part 1, the system was a star and the surroundings were the black hole, and in part 2, the system was a spaceship and the surroundings were the planet and the moon. A little preview of the result. In part 1, I found the mass of the black hole to be around 1.634 times 10 to the 34th kilograms, and in part 2, I found that the initial velocity of around 14,000, 37,000, and 0 in vector form x, y, and z meters per second had the spaceship uniquely orbiting both the planet and moon for around 600 hours before crashing into the moon. Both parts use a small set of similar formulas and forces. The first one was Newton's second law, which is A equals F over m, which can be also written as F equals delta P over delta T, which is the momentum principle. Kinematics equations for position and velocity were also used to update the moon and spaceship's position and velocity, of course, specifically in part 2, where final position equals initial position plus v delta t, and v equals VO plus a delta t. In this lab, we use only one force, universal gravitational force. This is negative g mm, which is the mass of the two objects times over r squared times the unit vector of r. And for this lab, we must also assume that all bodies of mass, the star, the planet, the black hole, etc., are mere points in 2D space, and no non-gravitational forces like thrust, drag, and whatever exist. Here are my experiment procedures. In part 1, I began with the starter code and edited the code seed and changed the position, velocity, momentum, parallel and perpendicular forces, etc. Then I applied Newton's law of universal gravitation and solved for the mass of the black hole, calculating the average value across all iterations of the calculation loop. In part 2, I began with the new starter code and edited the code to calculate all the gravitational forces and update the positions and velocities of both the moon and the spaceship. Then I found an initial velocity of the spaceship that results in it having unique orbital paths around both the moon and planet through just guess and check. Initial conditions are found on the left, and the top image is part 1, specifically delta t being equal to 86,400 seconds, which is 1 day, and the bottom image is part 2, where delta t is 60 seconds, which is 1 minute. Both GlowScript codes use the momentum principle and position and velocity kinematics formulas that I explained in the previous slides, and similarly, the force modeled is that universal gravitation formula, where in part 1 I solved for the mass of the black hole, and in part 2 I used it to find F net on moon and F net on ship, which can be broken down into their parts, where F moon is F planet on moon, F ship on moon, the sum of those, and the similar idea goes for F net on ship. And the arrows in part 1 represent the F net parallel, and F net perpendicular. In part 1, you can see these arrows get bigger when you get closer to the black hole and smaller when you get farther away from it. This is because force is inversely proportional to distance or radius. And in part 2, you can see the unique orbit of the spaceship between the planet and the moon. And in part 1, I forgot to say that F net or F parallel, radially parallel, has to do with the direction of the star, and F perpendicular radially, so tangentially parallel, has to do with the speed, change of the speed of the object in motion. All right, in part 1, although the mass of the black hole varied very slightly over time due to rounding errors and other differences, the computed values were very similar across t, and the average mass was consistent with Newton's law of universal gravitation. In part 2, although the orbit of the spaceship around the moon and planet isn't a perfect figure 8, the initial velocity chosen allowed the spaceship to exhibit orbital paths that are influenced by both the planet and the moon's unique gravitational force, obviously without crashing. Some sources of error include small inaccuracies in the code, like syntax, calculations, and definitely rounding, and then also guess and check method in part 2. But in general, there weren't as many sources of error compared to in-person experiments because there's not, that real world conversion to a digital. So the net force and the force and the rate of change of momentum are equal by the momentum principle, right? Because F equals ma, which is just Newton's second law. We can derive the momentum principle right now, where A equals delta v over delta t, and delta p equals m times delta v. So they're equal. By the same idea, the components of both force and the rate of change of momentum are also equal because they sum the same way, right? So the parallel force plus the perpendicular force equals the net force. If this imaginary system had a black hole, a star, a planet, and a moon, if I wanted to predict the motion of the entire system, what would I need to do to conclude in my computational model? Well, with a system with 4 objects, there would be 6 forces needed to be accounted for, since every massive object in that system is influenced by the force of all 3 other objects in that system. The dominant interactions would be the objects with the most mass, aka the black hole and the star. Thank you.